And so today I would like to introduce ESTCP project number ER-200716 on improving effectiveness of bioremediation at DNAPL source zone sites by applying partitioning electron donors. This project was led by Carmen Lebron. And Carmen, I will turn it over to you to introduce the project and your team. Thanks.
Thank you so much, Andrea, and thank you all that join us during this call. This is a bioremediation project that was funded back in 2007 under ESTCP, and the technology relies on applying partitioning electron donors, or PETs, as opposed to soluble donors such as lactate, to enhance the rate of dissolution from the DNAPL source zone area. Next, so we are in number 2. And I'd like to introduce the team who are also in the call. This project was led by myself, formerly with NASA's Expeditionary Warfare Center. Geosynthetic consultants did the on-site demonstration. Dave Major, Michelle McMaster, Corey Recta, and Rebecca De Prado. Kurt Pinnell and Natalie Capro, at the time with Georgia Tech and currently with Tufts University. They performed the batch and column abiotic studies to determine the PET's mass transfer properties. Dr. Frank Loeffler, who's also in the call, back then also at Georgia Tech and now at University of Tennessee, who conducted the biotic bench scale evaluation. And Mike DeLeese, the site manager for the selected site, which was NASA's Launch Complex 34 at the Kennedy Space Center in Florida. Next. So let me give you a bit of a background on what a PET, or a partitioning electron donor, is. Electron donors such as lactate and veg oil are usually applied to enhance dissolution. And the most commonly applied donors are in the category called soluble electron donors. These electron donors work by enhancing dissolution rates at the DNAPL water interface, where they facilitate biomass to establish. Why do they act at the interface? Mostly because they don't have the capability to penetrate into the DNAPL. But if they would, such as partitioning electron donors, there would be a much more close contact with the DNAPL. So by contrast, partitioning electron donors are electron donors that have the ability to partition directly into the targeted DNAPL. Examples of these PETs are N-hexanol and N-butyl acetate. These PETs penetrate the DNAPL instead of having to rely on the surface contact with the DNAPL, and this results in a much higher dissolution rate. So now that you know it all on PETs, the goal for this project was to apply a PET at a DNAPL source zone site and validate the enhanced dissolution rate caused by the PET. We also wanted to validate that the PET could partition both into and out of the DNAPL. Next, which is now view graph number 4. And these are our performance objectives for the project. One of the lessons learned was, as Michelle says, not to have these many performance objectives, because then you have to track all of these. Nonetheless, we had both qualitative and quantitative performance objectives to ensure that our goals were met. On the qualitative side, our main objectives were ease of implementation, also the ability to promote biodegradation, being able to keep the electron donor supply at an effective dose, meaning longer than soluble amendments, and the ability to be able to partition in and out of the DNAPL source. On the quantitative side, we wanted to deliver the PET to the source in a matter of hours, not days. We wanted to be able to increase the TCE dissolution at a higher rate than a soluble donor. And for that, we used data from a prior investigation in the same area using soluble donors that had happened a few years earlier. We also wanted to be able to produce degradation products at a greater production rate per donor consumed compared to soluble donors. And it was very important to reduce the mass in the source area by at least 50%. And we also wanted to be able to reduce operation and maintenance costs by at least 25% compared to soluble donors. Next, which is number 5. So we begin on with the results now that you know what we set out to do. The first task of this project was an extensive bench scale testing that occurred at Georgia Tech. As I mentioned, Kurt Cannell and Natalie did the abiotic studies, and Frank Loeffler did the biotic studies. We began our test design with these batch and column studies to determine partition coefficients and to decide which of the 2 available partitioning electron donors to use. Both N-hexanol and N-butyl acetate were options at that point. Through the abiotic studies, we determined liquid-liquid mass transfer rates, both under dynamic flow conditions and under abiotic columns packed with fine Ottawa sand, amended with a uniform distribution of residual TCE DNAPL. During the bench scale evaluation, 2 different PETs were tested, both N-hexanol and N-butyl acetate. And based on both the abiotic and biotic batch and column studies, we decided we would use N-butyl acetate. The results of these investigations are summarized in this ESNT journal article by Natalie and others. Next, which is number 6. I don't mean to go into the details of these abiotic and biotic studies, just to highlight the level of rigor of what went on. In this case, we're talking about the biotic studies that Frank performed. We had 12 bottles evaluating different combinations of electron donor and electron acceptors. All of these treatments were prepared in triplicate along with 3 additional bottles as negative controls. And we tested 2 different concentrations of a DNAPL surrogate, which was a combination of TCE and TCA. The different concentrations were 5 milligrams and 200 milligrams of that surrogate DNAPL. What worked best was the N-butyl acetate, which dechlorinated 100% of the surrogate NAPL, as we can see. The other thing we realized, that resulted from this study, was that the results indicated that a single PET injection could persist in the source zone even after treatment would be completed. Next, number 7, which is, let's talk about a bit about the site now. We are all familiar with the NASA's Launch Complex 34 at the Kennedy Space Center. And this is hotspot number 1. Their source had been there for over 40 years when we began working at the site, but TCE concentrations were still around 30 parts per million in the center of the hotspot. Next, number 8. the site biogeochemistry was ideal for the demonstration. Geochemical conditions clearly demonstrated reducing conditions. There was already ethane and methane at the site, and both biostimulation and augmentation had been demonstrated at the site before, so we could use that data for comparison purposes. Next, which is number 9, very briefly. What we set out to do was go in, do baseline sampling, including assessing mass flux, amend the test plot, and then evaluate performance based on mass flux of the TCE, formation of degradation products, the PET longevity, and certain microbial parameters. If you look on the right-hand side, the diagram of the site, the pointy blue dots seen here are the injection points where we injected the PET using direct push technology. And we then recirculated water to mix the PET with the contaminated groundwater and enhance contact. We extracted at the 2 extraction wells, and we'll see that in much more detail in further view graphs. And then we re-injected the treated groundwater through the injection wells on the periphery. Next, so we have here the cross section, the side view. We can see that we have 2 different sweet zones at the site, one above and one below the clay horizon. So we instrumented and operated each of the sweet zones separately. The red zone there in the middle, that's pretty much the clay horizon. Actually, I have this one right there. So each sweet zone was instrumented with a single central extraction well from which integrated groundwater samples were collected routinely to monitor the average concentration of several dissolved constituents. Keep in mind that the PET was injected using direct push, so this system was there just to recirculate the water and mix. Where we wanted to inject was pretty much at this clay zone because we knew that's where most of the TCE resided. Next. Okay, so this is an MIT profile from the center of that hot spot back in 2009. And what we're seeing at these steps, it's exactly where we want to work. Our goal was to target that zone between 30 to 60 feet for the PET addition because based on the observations from the MIT investigation, together with the groundwater concentrations, DNAPL was inferred to be present in that area. Next. So again, we can see here in more details the 20 spots where we injected the 2 extraction wells and the 10 injection wells, as well as the 3 cluster multi-level monitoring wells. Next, which is the recirculation system, again, only for mixing. Each extraction well operated at a relatively low flow rate to maintain an inward hydraulic gradient and collect representative groundwater from the aquifer on each side of the clay horizon. And then the extracted groundwater was analyzed for VOCs to establish the baseline flux. Next, we ran our system using solar power, which even in sunny Florida, it still had some glitches. Next. We mixed the PET with water. We learned a valuable lesson in an earlier application in which it was not mixed, and we ran into issues with the well. So before we injected the PET, we mixed it with water, and then we injected 34,000 gallons of that solution containing MBA at 3,000 milligrams per liter, and two different tracers, bromide and iodide. And the reason why we had the two different tracers was so we could track what was going on both the top and the lower aquifer. Next, which is number 16. This is just to show how we injected the PET. Again, direct push was used to inject through those 20 points in the hot zone from 23 to 60 feet, 62 feet below ground surface. And this approach delivered the amendment solution throughout the pore volume of the plot all at once, rather than relying on effective transport in a recirculation mode, and allow the amendments to be preferentially delivered to the plate layer. Next, this was just a field demonstration schedule so that you have an idea what we did and for how long. After we installed the wells and did system shakedown, we did a baseline characterization of both the soil and groundwater. And immediately after that, we assessed mass flux and then amended the site with the PET and tracers. Next, which is number 18. I'm going to first summarize the results and then later get into details in a few additional view graphs. So in summary, all of our performance objectives were met. We were able to introduce the PET into the low permeability location using direct push and promote dissolution and biodegradation. The D-helicoides densities increased, and a year after the only injection we did, the donor was still present, as evidenced by the high TOC and volatile fatty acid levels. And the PET partitioned into the DNAPL and increased the dissolution rate, as evidenced by the increased mass flux, at a higher rate, which was achieved years earlier by a soluble donor. Next, which is number 19. So when it comes to our performance objectives and having met some, let's tackle the qualitative performance objectives first. So the process was easily implemented using direct push and off-the-shelf technology. The PET was able to promote biodegradation, and the fact that a single injection resulted in elevated TOCs and BFAs when we discontinued monitoring confirmed our objective for donor longevity. We were able to confirm that the PET partitioned into the DNAPL through lab studies, however, not in the field due to the low DNAPL saturation in that hot zone. We also confirmed that the PET partitioned out of the NAPL at a suitable rate as sustained by TOC and BFA concentrations throughout the demonstration area. Next, 20, which is our quantitative performance objectives. We were able to effectively deliver the estimated required PET solution, which had been estimated to be 33,600 gallons in a matter of hours. Based on the tracer test, the PET was reasonably well distributed in the area. Also, our performance objective dealing with increasing dissolution over 50% of what was achieved earlier with a soluble donor at the site was generally achieved as evidenced by the increased mass flux and increased proportion of breakdown products. We were not able to state with certainty that there was a greater production of degradation products per donor consumed. Yet we were able to validate the reduction in TCE mass within the source area by achieving higher than 50% reduction, and we were able to confirm that the reduced O&M costs will be achieved compared to non-PET costs. Next, this is one of those plots that shows plenty of data. So we have that these are up here. You see the different phases, the baseline flux assessment, the biomass growth, the main phase, and the interim measured recirculation. We are calling this interim measure recirculation a bit different because that was not really part of the validation program, but the site did select this as the interim measure recirculation, and they continue to collect data, so we are presenting it to you as well. On the x-axis is the date and the sampling event, and on the primary y-axis is the cumulative micromole per chlorinated VOC from the extraction well, specifically here ER-200716. Then we also have a secondary y-axis where we have the dehydrocolloides and the BCRA gene copies per liter. So from all of these, what we gather is, and what we can see is that the PET addition increased the dechlorinating biomass and sustained it for more than the 26-week evaluation period. And we also see that the start of the demonstration that the primary VOC was 60 CE, and by 12 months it was dominated by vinyl chloride and increasing amounts of ethane. Anything else you want to add, Michelle, in this one, or Dave? They're muted.
No, sounds good so far.
Okay.
Yeah, that's, you hit the high points, Carmen.
Okay, let's go on to number 22. This is the same type information, only for the lower VOC zone. So the well is ER-200716, and we see similar trends to the what we've seen in the upper, but with lower initial mass and higher overall ethane formation. Next. This plot shows the range of organic acids over the demonstration period. At early time, the degradation of NBO acetate could be observed, and then acetate, butyrate are consistently present. Next, which is number 24. Here we're talking about the source zone of the chlorinated VOC's mass in that area. So the slide provides an estimate of the mass remaining at defined sample events, which are listed down here. April 11th is the end of the baseline phase. August 11th, which is the end of the biomass growth phase, and right before circulation, and then October is about 6 weeks into the circulation. So February 12th is the end of the DEMVAL period, and there were 2 other sample events after that. So those dates are selected because of that significance significance. The stacked bars show that the total VOC mass estimated in the demonstration test area. We can see that mass over time is decreasing. Also the A graph plots just the dissolved phase mass, and the B graph includes the sort mass, which was calculated from the FOC and the retardation at each compound based on organic matter. This indicates that the PET addition promoted mass destruction. Next, which is number 25. So for the cost and performance report, we had to create a comparison to a technology that was comparable. And the closest technology to PET is remediation using emulsified vegetable oil. Therefore, we use that for our comparison to the PET. And to set up that comparison, we established this scenario, which is close to what we had at LC34. We are assuming for both cases that the mass in both scenarios is about 500 kilograms TCE. We have a source zone volume of 48,000 cubic feet. We are assuming a 30% porosity. The source zone pore volume is also the same in both scenarios, or 14,400 cubic feet. And now the difference lies in that the stoichiometric donor demand is 83 kilograms for the PET and 64 kilograms for the emulsified vegetable oil, which then translates into a target mass of donor into the formation of 620 kilograms for the n-butyl acetate and 1,880 for the vegetable oil. Next, which is number 26, I think. So comparing the costs, some costs remain the same. Treatability studies, monitoring well installations, donor application, and system monitoring. But the total cost for the n-butyl acetate is about $100K cheaper, mostly because of savings being less cost for the electron donor, and because it is more effective, there is reduced monitoring time. Next one, which is scale-up issues. Are we there? Okay, there we go there. Okay, we don't see any issues associated with scaling up this technology. In fact, everything from instruments to tools and systems that we use is currently commercially available. Lessons learned. We had an issue in micropound site in which we poured the pure phase n-butyl acetate into a well, and the well casing, which was PVC, melted. And Michael was very nice about it, but we learned our lesson. We also used the solar energy, and that was suitable, mostly because it was in Florida, but even then it had downtimes. And one of the things with this technology, but it's also true to other technologies, is that we should have a very good understanding of where the source zone mass is. Next, available tools and publications. The biggest thing that came out of this was an ESNT paper by Natalie and others in the team. And for us, also personal achievement was the fact that Mike DeLeese decided to use this technology for another period of time because it was being so effective. And we also have several publications and presentations. And with that, I would entertain questions.
Great, thanks. Is there any questions?
This is Linda Fiedler at EPA. Hi, everyone.
Hi, Linda.
You know, this has been out there for a while. Have you seen any impact on, have you seen any increase in full-scale application of this technique?
I'm going to leave that to Michelle and Dave. Personally, I have not. And quite honestly, I look at the data and wonder why, except maybe we have not been as aggressive tech transfer-wise as we should be. Michelle, Dave, anything you want to add?
This is Michelle. I know that one of the commercial vendors of EDO is still trying to develop a long-term electron donor mixture, slightly different than the NBA that we used for injection. And I can follow up with him and see where he's at on it. We really kind of need to, I think, keep pushing it back out to the electron donor vendors for them to encourage its use.
So just a follow-up. So you're saying that it's not truly commercially available at this time? You couldn't go out and purchase this particular amendment?
You can. You can go out and purchase just straight N-butyl acetate, and you could inject it. One of the emulsified oil vendors wanted to try and put other enhancements on it to see if they could make it as a more commercial product, and that was where they were sort of going with it. But you could just use the N-butyl acetate itself.
Where would you buy it from? Like, are there different grades that cost-wise would?
So commercially, it's a primary product in a lot of chemical manufacturing. So we bought ours off of, I believe, Corey, remind me the name of the company. But yeah, we just bought it off of a vendor company in California.
So what you're saying is because this isn't a patented, profitable technology, we're not seeing it out there.
Potentially,
it's
yes.
not marketed. It's not marketed by someone who would profit from its use.
Yeah, potentially.
That's very interesting.
So Carmen, what innovative tech transfer ideas do you have to push this forward?
I think Michelle hit right on it as to work with vendors. I can see conflicts of interest when that happens. You just got me thinking at this point. If it's really a commercialization issue, or is it really other vendors have vested their own money on their own products, therefore what it's in it for them to market this. This was Dave's idea, and it was something that had been tested out by the Sabre partially. Whatever happened with that project, Dave? or
A lot
Michelle?
of things happened with that project. They treated at the Sabre project in Britain. They managed to remove about a ton of chlorinated solvent from the test cell, and the publications are coming out on that still. But the idea there, what they were kind of looking at that case, there were mostly vegetable oils they're looking at, and the idea came out of just from noticing obviously the partitioning between vegetable oils and chlorinated solvents, and so we thought about why don't we look at it the different way around and say get something that will actually dissolve more into the chlorinated solvents in the source area rather than partitioning it back out into solution.
Are there any other questions? Okay. Thank you, Carmen, and thanks everyone else from the project team for taking the time to give us this final debrief. We do appreciate it, and looking forward to getting it posted so others can listen in. Thank you.